All right, we're going to complete this problem by focusing on the last two parts of this question. And that begins with finding the atomic packing factor. And so that is defined as being the percent of space occupied by the copper atoms, or the fraction of space occupied by copper atoms. And so the way to do that is to simply calculate the volume occupied by those four copper atoms. Remember, we figured out that there were four atoms inside the unit cell, and then we're going to divide it by the volume of the unit cell. So this atomic packing factor, we know will be a number somewhere between 0 and 1. In fact, we know it'll be higher than 0.52 because that's the packing for simple cubic, and that's the least dense of the cubics. So we're looking for a number somewhere between 0.5 and 1. So this atomic packing factor thus will be the four atoms that we have inside the unit cell times the volume of a sphere, because we think about the packing of these atoms, even though, of course, there are electrons spinning around, but they basically pack as hard spheres, or we can consider that to be how they pack. The volume of a sphere is 4/3 times pi times the radius cubed. All right, so that's going to be the fraction, the volume occupied by the copper atoms, and then the volume of the unit cell will be, of course, it's A cubed, A times A times A. We found an expression for A of 4r over square root of 2, and when we put real numbers in there, it was 0.36204 nanometers. And I'm going to use the left version because it'll just be easier, because I have r cubed in the numerator here, right? So we're going to take 4r over root 2, and we are going to cube that. All right, so let's just simplify that and solve for it. So we will have 4 atoms times the 4 from the 4/3 pi r cubed times 1/3, or maybe we can even write pi over 3 times r cubed in the top part. I'm just kind of rewriting it in an easier way. On the bottom, we've got I'm going to expand. Of course, 4r cubed is 4r times 4r times 4r. So we will have 4 times 4 times 4 times r cubed. And then the bottom part of that, when we cube the square root of 2, we will get square root of 2 times square root of 2 times square root of 2, which is 2 square root of 2. And then that will flip over to the top side. So I will have a times 2 times square root of 2 on the top. And I'm doing it this way so we can see what easily simplifies. So r cubed over r cubed simplifies. 2 of these 4 simplify. And so the expression then becomes, let's see, we have a pi over 3. And then we have the 2. So we're gonna have the root 2 is going to be left over for sure. And then we have 2 over 4. Which is the same as 1 over 2, so there'll be a 2 on the bottom. In other words, it's pi times the square root of 2 over 6. And that number is, when you pop it into your calculator, 0.74. And that is the correct answer. It's always nice when you end up with the correct answer. In other words, the efficiency of space being filled up by the copper atoms is 74%. The atomic packing factor is 0.74. There's lots of ways to think about that. Another way to think about it is that 0.26 of the space, or 26%, is empty. And that makes it possible for us to do interesting alloying things with that empty space. All right, let's move on to part C. So we've done B, let's move on to part C. Calculate the theoretical density, all right? And so theoretical density is best thought of by considering the units of density. All densities have units in grams per centimeter cubed. Remember, water has a density of 1 gram per centimeter cubed. Metals have densities of 7 or 8 or 9 or higher grams per centimeter cubed. And so, you know, I'm seeing the grams here, and I'm realizing we need another piece of information. We need we need to know the atomic mass of copper. So copper's atomic mass is 63.5 grams per mole. And as I like to do, I'm going to solve this with dimensional analysis. I'm going to, whatever this density is, we're going to need grams in the numerator. So we're going to write 63.5 grams because that has grams in the numerator and moles in the denominator. And now I want moles to cancel out. So I will write 1 mole in every 6.022 times 10 to the 23rd atoms. Okay, so now I've got grams per atom. That's not grams per centimeter cubed, but I've just been thinking heavily about how many atoms there are in a unit cell. And I do know that there are 4 atoms in an FCC unit cell. And for this unit cell, I do know that the lattice parameter A is 0.36204 nanometers. That's an NM. And so if that's A, I then have to cube A. So now I have the atoms cancel out, and I have units of grams per nanometer cubed, and now I just got to convert my way into centimeters cubed. So there are 10 to the 9th nanometers in a meter. Got to cube them, so that means there'll be 10 to the 27 nanometers cubed per meter cubed, and then I need to get myself into centimeters, so in every meter, there are 10 to the 2 or 100 centimeters, and that is to be cubed. And so we have this 10 to the 27th divided by 10 to the 6th. So this whole mess here is a factor of 10 to the 21. And that's good because it helps offset this Avogadro's number. And so if we just kind of pop this into our calculator and see what we get 8.89 grams per centimeter cubed as our theoretical density. And in case you're curious, how does this compare to the actual density? The actual density I see as being 8.96 grams per centimeter cubed. So it's a little denser than its theoretical density, which is a little surprising to me, actually, but that's what the numbers tell us. All right, thanks very much. That's it.